Oh, this is EE380, recording at October 26th. And this is a presentation about the Semiconductor Incubator Group Silicon Catalyst, about how to build a semiconductor company. Silicon Catalyst has a interesting business model for providing incubator services and a mechanism for keeping the cost of building a semiconductor bounded. In any case, it's a great group of people, and we're going to start off today by examining, well, their process and how it all works. The CEO, Pete Rodriguez, is going to provide a brief introduction and then continue on. If you're a discussant, please hold your questions to the end and raise your hand when the time comes, and we'll go through your questions and listen to your comments. In any case, Pete, you're on. Thank you very much.
Thank you, Dennis, and thank you, Stanford 380, for having us. I'd like to point out that last time I gave a lecture physically at Stanford, they shut down the campus the next day. So I don't know if that was me or COVID, but I'll introduce myself briefly, and then the two presenters, Mark Ross, who's going after me, and Raul Camposano, who's going after Mark. And then I'll also introduce the other members of our team that basically drove to put this together. Rick Lazansky, our founder and chairman, who's participated in 15 startups since he left Stanford in 82, 83. And I've worked with, this is our third time working together. And Laura Swan, who pushed us to do our slides, and also has been an entrepreneur, an angel investor, and co-founder of the battery at Berkeley with Rick. So thank you both for driving this along with Dennis and getting us up here, and thank you for creating great slides. So a quick introduction on myself. I'll also introduce Mark and Raul, and Mark and Raul, if there's anything you want to add or highlight that I don't cover, please do so. So I've 35 years in the semiconductor industry. The first 10 were all deep technology. I did a startup where I was the head of engineering, and the startup failed, and it didn't fail because of engineering, it failed because of sales. So I went and got a lobotomy and went into sales, and figured that next time that I did a startup, I would understand that concept. This is my fourth startup, probably my last. Along the way, I've also, I ran a public semiconductor company, and I ran $1 billion business for NXP Semiconductors prior to semi-retiring for 2 years, and then joining Silicon Catalyst. Let's see, Mark, who's going next? Stanford graduate, I think both bachelor's and master's. I won't hold that against you, Mark. And has had an amazing career, and has been one of the most valuable advisors of the 180 advisors that we have from the semiconductor industry at Silicon Catalyst. Mark has worked as an architect for Steve Jobs at Next. He's worked as an architect for Andy Bechtolsheim at Granite, I believe, and then on at Cisco. And then he later worked as Chief Technical Officer for TJ Rogers at Cypress. So 3 crazy dudes, really smart and crazy dudes that you've worked for. And also you've done a bunch of startups along the way, and currently are helping 2 or 3 of our startups. So it's great to have you do the technical presentation there, Mark. And then Raul was a professor in Germany, was recruited to come to the US. I guess you've done work at Bell Labs and other areas too, Raul, and then went off to do 20 some years at Synopsys, including CTO. Raul's also an adjunct lecturer. I don't know what that means. English is not my first language, but he's also an adjunct lecturer at Stanford. And I hear his classes are very good, so I'll have to attend one of these days when COVID is over. And then Raul has done 3 startups since leaving Synopsys, and most recently his startup Sage was acquired by Applied Materials. So Raul will be going after Mark, closing up today's presentation. So I'm really honored to be on this panel with these 2 fine gentlemen. And with that, Laura, let's start the presentation, please. So before I cover some of the details on this slide, if any of you are interested in starting a startup, specifically a semiconductor startup, but really any technology startup, expertise, either technical expertise in the space or deep market expertise, it would be actually better to have both, if not in the one individual, then in the founding team. I think starting in areas that are not your areas of expertise add just one more level of difficulty in doing a startup, which is already quite difficult. The next thing I'd like to mention is that the number one thing that venture capitalists look at is market. I had one VC tell me 20 years ago that the 3 rules of real estate are location and the 5 rules of venture investment are market size. So clearly they like to see markets. And one focus in this area is that it's not, we have entrepreneurs that put up slides, and we've looked at over 350 companies in 5 years at Silicon Catalyst, and they'll show the IoT market as, 80 billion. Well, clearly they're not going with one chip after the entire IoT market. So you really need to look at that you're specifically going to go after. What is the size of that? Next, there has to be a real pain in the market. And like to point out that you get paid for solving pain. So the other comment there is that when is this pain going to be solved? If you're going to have a solution in 2 or 3 years, is there going to be a relevant pain that you're solving there, and you're solving it superiorly to someone else? So if we go through the slide, you got to take concept of looking at the competition. You need to have guidance, talk to multiple advisors, especially those that are experts in this area, experts in go-to-market. You got to talk to a lot of customers. And when talking with customers, it's really clear to understand where their problems are going to be in 2 to 3 years. Steve Blank at Stanford has put together a program along with others that the NSF teaches called, and they insist that you talk to 100 customers. Now, in certain solution areas, there are more than 100 customers. Okay. And finally, you need to talk to investors. If I put this business plan together, if I can have this level of value proposition, if I can have this level of pain solved in 2 to 3 years, will you invest in this venture? To the customer, will you buy this solution? And one of the most important things in doing this analysis is not what the customer tells you they want, but what the customer is willing to pay. So that part is really, really critical and really difficult to ascertain. And so at XR, when I was running that company, we acquired a startup called Natarian. Natarian had come out with either the first or second 10 gig Ethernet solution. They had gotten Hewlett Packard as a customer. They had received an offer for acquisition for $300 million, and they turned it down. By the way, you get a good offer like that, just take it. You could always do another startup. In the second generation, they only listened to one customer, and I acquired that company for $11 million. So listen to your customers, really figure out where their pain point is going to be when your solution is ready. And I think Mark used the quote in his comments to this slide is like Wayne Gretzky said, skate with the competition where the puck's going to be, not where it is right now. So move where the competition is going to be, where the solution is going to be at the time that you're ready to deliver a solution, not where it is today. And you got to have a clearly defined value proposition. If you're competing with an established player, you got to have a significant advantage, probably 10x, in order to win. So that's my guidance on all of this, but very clearly get advice, speak with customers, speak with investors, understand the market, the competition, and where things are going to be at the time that you launch your solution. And one more point, Bill Gross down the Southern California Incubator King did an analysis of 200 successful companies, 100 of his and 100 in Silicon Valley. And the number one thing for success was timing. Team was number 2, but timing was number 1. So the market window that you're going to be hitting is very, very important. Okay, look forward to questions at the end on this. Let's move on to the next slide, please. Okay, so there are many questions to identify in building a semiconductor company. Do you have a product worthy of building a company? So if you look out into the future and you say, okay, I deliver this product, I deliver this value proposition, I have 10 customers that are buying it in production. I am getting the following, price for my product. And that's really difficult. Value pricing, you can do value pricing at the beginning when you have a clear advantage. As you get others to compete with you, it becomes more commodity pricing. So when all of that is said and done, when you create a picture of that, is that enough to drive a standalone business? If the answer is no, then you have to determine, okay, is this enough to get to cash flow positive and create something that will be of value for someone to acquire? Second, are there enough customers? If there's only 2 or 3 customers, then you have to at least win one of them, and that has to be sufficient to make your business go. If the answer is no, then don't spend a ton of time and money. Find something else. And then where are the companies today? Where are they going to be in 2 to 3 years? Is there another startup that you don't know about or in stealth mode? And that's where you have to go to industry events, conferences, and talk to people. If you talk to customers, they will typically know, because those companies are also trying to figure out what the answers are. Okay, next slide, please. So what kind of company would you like to build? So clearly in the semiconductor space, and today at Silicon Catalyst, we take any type of semiconductor solution. What we mean by that is a chip plus software, a chip plus a system, or a chip plus a sensor, or any combination of the above. And now we've extended that to intellectual property and to MEMS and sensors. Typically, a solution is more sticky than just a chip. So even if you have, say, an interface chip that's going to go for 50 cents, if you have really good software drivers, those drivers will make that interface more sticky than if you don't. Clearly, as you move up the value chain in terms of solution, the more the software that you have, the stickier your solution, the more valuable your solution, and the harder it is to replace from a given socket. In today's world, in a lot of commodity and semi-commodity products, you not only have to win the product, say at the system provider, but then you have to go win it again at the company like Foxconn that's going to build it. And they operate on such thin margins, they're always looking to replace commodity providers with others at a lower price. With companies like Apple and Microsoft and Intel, you're somewhat protected because they define who you can use. But still, the more the value that your solution has, the better the asking price you're going to get, the better the value pricing. So you want to be solving a key problem for the customer. If it's just, if it's a minor pain point, they may just power through it. They may not completely change their design for a smaller company and take that risk. So really have to solve a real pain point. Okay, moving on to the next slide, please. So business plan and go to market. This is very, very critical. All of these items will drive your costs and how much money you need to raise. For example, depending on the solution that you have, the expertise, the problem you're solving, you may be able to raise money with PowerPoint. So we have a company we recently talked to that raised 20 million with a PowerPoint presentation. That's highly unusual. In 90+% of the cases, you're going to have a lot more than that to raise money. And you're probably going to raise a couple of $1 million in seed to get to the next step, which is typically some type of minimum viable product or a prototype. And it's much easier to raise money with a prototype as part of a system. So one more thing to drive here before I get into the specifics of this slide, and that is today, even if you're building a simple interface product that's 50 cents, you're going to have to showcase it as in an entire system. You're going to have reference designs of how that fits in with Intel or Apple or Samsung or whomever that you're trying to sell into, and have a complete solution, even with software. Even if it's not a production-worthy solution, but it has to be good enough to show that your chip works at the performance and at the data rate and so forth, at the power levels So even the simplest products today have to have a reference design along with them, and that has to be part of your plan. So, but when you look at the product, there are many points here. Mark's going to go through this in much more detail than I am right now. So, but clearly what the functionality is, the intellectual property from outside that's going to require, what are the non-recurring engineering costs to get it to production? What will your cost of goods be when you're in production? And how will you go to market with it? Is it 5 salespeople going to 20 customers? Is it a distribution and rep network? Is it a combination of the above? And those are all key questions that you're going to have to ask. And finally, how do you really go to market, right? And for example, I'll give you a solid example. At NXP, we were doing 10 billion in revenue. We had a power business, we had an interface business, but we wanted to go into a charging area where we didn't play. The cost of doing that, even for a $10 billion company that already had customer relationships, was to build a prototype, and we spent several $million doing it, that was a little bit better than what was available, and it was only to get us in the door of those meetings that they would treat us seriously and say, okay, here are the features we'd like you to add for the next generation. So depending on the market, depending on the customers, you may have to have quite a bit of collateral in order to get in the door and take a chance at the next generation. Okay, next slide. Okay, so why now? I think we've already talked about this in the previous slides, but your product development can easily take 2 to 3 years. Oh, I'd like to add that there are different markets with different time constants. If you're selling into automotive, it's in several years. If you're selling into communications, it's several years if you start at the right point. Because if you start close to when another cycle is going to be, when people are going to go from 10 gig to 100 gig or whatever, you need to decide when you're going to cut into that market and then work back from that. If it's aerospace, it could be longer. If it's consumer, it could be 6 months. So each market that you go into has a different time constant and a different point that's important for you making your decision. Okay, and clearly, especially for digital designs, but even for analog designs, for digital designs, you can build a prototype and show people with an FPGA plus, an off-the-shelf mic or a microcontroller already included in that FPGA. In analog, in some cases, you can buy off-the-shelf products, off-the-shelf radios, and other things to demonstrate at least a high-level functionality of your product. Again, it's a little harder to do that. But clearly, you want to understand the market window and work back from that, and make sure you have enough slack that you're going to be able to meet it, because things always slip. Next slide, please. Okay, so I think we've already covered this, and that is you want to hit the market at the right time so you can maximize the number of units. Clearly, as the market becomes mature, you're going to be able to charge less for your product. So you got to have a cost reduction strategy built in so that you can maintain your margins, or at least get close to maintaining your margins. Okay, next slide. Typically, most of the entrepreneurs that we deal with are 1 or 2 persons, so they're typically both technical. Clearly, if you're going to have a company, you need more than that. You need operations, you need general administrative, you need technology, both creating the current product and looking forward to the next product. Clearly, when you're 2 guys in a garage, that's hard to do, but you need to have a plan for putting together your team together. And you have to have a company in mind. When I get to this point and I have 50 employees and I'm paying them an average of this, and cost of goods are costing this, I need to have a revenue of this plus a profit of this. And all of those models have to make sense. And every entrepreneur we talk to obviously has a hockey stick in their plans. Make sure that that hockey stick is underpinned with some reality, right, as to what you can get for your product in what time frame. A design win is very important. Did I get a socket where? A socket on an iPhone is vastly different from a socket on a Mac, vastly different from a socket on some Microsoft or Intel products. So how sticky is that socket? How long will I be able to keep it? So these are important questions to answer, and you need a solid team to get to success. Yes, the market window may be the most important, but you can't get to the market window without a solid team. So be thinking of the team. What are your strengths? And then what are the complementary strengths that are required to build a good company? And now I'll turn it over to Mark to building an IC. Thank you.
Thanks, Pete. And it's wonderful to be here. One thing that Pete was saying that is really important is that often technologists, which I am one, we focus on the technology. And to Pete's point previously, a successful team requires a number of different disciplines. And those disciplines are often in areas that you don't have strength. So that's something to keep in mind. So what we show on this particular slide is two different paths to how to build an IC product. Pete covered the first one a little bit by saying that depending on your type of design, you might actually be able to use off-the-shelf components to get to a demo. A thing that reiterates a point made earlier is that demo, regardless of whether it's the first or the second stage, the demo is an important proof point. It's a proof point both for yourself, and it's actually a proof point for investors. And finally, it's a proof point for customers. And that connection with the customer is absolutely essential because they're the ones that guide what you should actually be building. So as I say, the difference between the top and the bottom flow here is whether or not you can, in fact, use off-the-shelf components to go build the solution that you're trying to do. But in any case, you end up going through the chip design that you're doing, the demonstration phase, and finally the go-to-market. So let's talk about the types of chips that there are. Next slide, please. So what I've done here is simplistically, I've defined three types of chips that you could potentially be building. One of them is analog, and I'll mention that pure analog chips are extremely rare these days. You could have a digital design, or you could have a mixed signal. It's equally critical to note that every chip that you're building, even if you think it's purely digital, is actually analog underneath it. Nobody bothered to tell the transistors that they were digital. And in fact, it's only through levels of abstraction and constraints that allow us to build a digital chip and treat it purely digitally. So we'll talk about this in the next slide. And it's really talking about the different layers that you've got. I'm going to go through this a couple of times in the different flows. So what you see here is architecture through to the masks or the physical design that you're doing. On the right-hand side, what you see are the tools that are helping you to move from one layer to the next. And on the left, what you see over here are the tools that are helping you to verify that transition as you move from one layer to the next. So with the architecture phase, for example, build out, please. So what you see at the architecture phase, that's one of the phases where you often have custom tools. So by custom tools, I mean that you may write C-level models of what it is that you're trying to build. And at that point, you may go into a high-level synthesis. So you have different methods of getting to the register transfer language if you're building one that has digital design in it, or going to the circuit design phase. But again, at each one of these stages, you have either synthesis, some kind of a tool that is helping you to move from one phase to the next. On the verification side, build out, please. On the verification side, there's equally a large number of tools that are helping you to validate that each one of these layers is actually functionally correct as you move from, say, register transfer language to the circuit design. Next slide, please. So what you see here, the point about the tools is that there are a huge number of tools that you're going to end up using as part of your design process. And in fact, there are 30 categories of EDA tools defined by the ESDA. These are in the levels that we said, the verification and the synthesis. There's a lot of them. One point that I would make in here that I think some people overlook is that stitching together these tools and some of the custom tools that you will need to write in order to be able to display, to analyze the data that you get from one of these commercial tools is going to be an important part of your process. So don't think that just because you've got a set of tools that you're done, you're going to need to figure out how to get those tools to work together as one cohesive block. Next slide, please. Back to the flow picture that we had, I'm showing a different view of it here. I call this typical, But as anybody that's built chips will know, there is no such thing as a typical flow. What we show in moving between these various phases is a set of arrows on the bottom that are the linear flow, where you design an architecture, you code up the RTL, you synthesize it, it creates gates, you move into a layout phase, and then ultimately you tape the chip out. It goes to fab, get through test and debug, test automation, you sell it, make a lot of money. Everything is wonderful. The problem is that the real world doesn't work this way. And what you see on the top are a number of back arrows that show you moving from a phase that you were at to a previous stage. And as the arrows are showing, you can actually move all the way from layout back to architecture. It's rare, and if you've done your job right, you shouldn't have to do this. But keep in mind that that backwards flow is a part of this entire process. It's also critical to note, by the way, that when you're moving through this flow, the most important thing that I can suggest that you do is tape out early and often. And what I mean by that silly expression is not that you actually tape out your chip multiple times, but that you get through the entire process as early in the design flow as you possibly can. And the reason for this is the whole concept of unknown unknowns. You don't know what you don't know until you get all the way to the tape out phase. Similarly, frankly, when the chips come back, what you need to be very careful about is if something doesn't work the way that you expect it to, keep in mind that if it's a digital chip, for example, you may have mistakenly thought that everything in that chip was digital. But if you had a phase lock loop in it, if you had a SerDes, if you had something else, there's an analog block at work there. And if something's going wrong, make sure that you go back and test the assumptions that were built into it that suggest that you can box that in a particular way. Next slide, please. So what we're going to do at this phase is switch gears a little bit and talk about a couple of scenarios and give you 3 examples. And the point of this particular slide is that you have a line chart on the bottom that is showing each one of the phases that we talked about and the duration that you would go through for each one of those phases. So again, you're seeing a linear progression of time on the bottom. The orange graph that you see here is the per month expenses. I want to emphasize here that this is labor cost only. And this will become a theme later, but what we're doing here is we picked a reasonable staffing and a reasonable cost per engineer. And so what you have here is that the costs per month are going up and down, and there's a cumulative cost that's happening in this slide. Now, one point that I will make, this is going to become obvious when you get to the next one, is that if you look at the monthly expenses, you'll note that they go up, but that they also come down. This is possible if you structure your company in a way where you have contract labor. So that means that when a particular phase is done, you can actually no longer need that person, so you're not paying for them. So next slide, please. If you look at this second scenario, what we're doing here is this one is, I'm not necessarily going to suggest that either one is more realistic than the other, but this is a different timeline where the first 3 phases, instead of taking 3 months, are taking 6 months each. It also is different because what you see here is what I'm calling accumulating staff. So what I mean is this: if every person that you bring into the company is an employee, and you're paying them whether they're doing, whenever you get them in, you're paying them, the people that were doing architecture during the RTL and the synthesis phases. Now, what I've done very successfully is that the architects are often the ones who know how the design is built better than anyone else. So you can often use them in other roles, such as verification. They're a wonderful resource for that. Next slide, please. So now what I wanted to do is to shift gears and show you 3 different examples. So these are emphasizing that what we were showing in the scenarios are realistic. So this first example is taken from a silicon catalyst portfolio company that I actually know quite well. It's showing you that they spent longer than what we've listed before in the architecture phase. So figuring out what it was that they were going to build. Their RTL and synthesis phases were about what we've shown before. And what you see here is that their expenses definitely do go down. So they were following that model of using contract labor for it. Now, a thing to keep in mind here is this is an example where in a span of a couple of years, they have spent roughly $2 million in labor. As the CEO of Trimito said, he believes that with reasonable funding, and he defined that as $3 million, a team of 10 people can get a chip done in 2 years. So that's something to just let that soak in, that it's roughly $3 million and a couple of years to get done. Now let's go to the next example, please. So this one is a chip that was mostly analog, another company I'm familiar with. What you see here is a completely different set of phases. So this was a company building a device that was mostly analog. And so for them, they did system and circuit design during the first phase. Then they moved to a layout, post-layout sim, and then finally the verification and testing. This was an extremely small team, so you notice that the cumulative dollars spent on this is quite a bit lower than the scenarios that we've shown or the previous example. It also shows that they were able to get to a chip in 12 months. One thing that I should emphasize on this is the accomplishment is absolutely incredible. This was a test chip, however. And so one of the things that you need to separate in your mind is the difference between something that validates what you want to do and something that you can actually sell to customers. Next slide, please. So in this third example, what we have is a chip that is almost exclusively digital with the caveats that I've mentioned before. And again, there's a little bit of a repeated theme here that while we said that in the longer scenario, it takes 6 months, most of these companies are showing that it is around 6 months to go through the architecture phase. And in this example, they have, I don't know that I had quite accurate head count on this. So this again is a less expense, but keep in mind, this is only showing you the 12-month window. So everything, including tape out, frankly, is not included for this particular example. Next slide, please. The last part after showing you these examples that I wanted to do is this is a way of reminding me with these 3 icons of some important considerations for you. And so they're just memory tricks for me so that I could remember what it is that I should be advising you at this point. The first one on the left is kind of obvious. The one on the far right is less obvious, and we'll get to that in a minute. Checklists are an important part of designing these ICs. They're a way of capturing the collective understanding, both as a company grows and progresses, but also the knowledge base that you come in with from the people that you put on your staff. So a checklist, the one critical point to keep in mind is that checklists are a means to an end. They're not the end. I've worked in companies where people end up getting overwhelmed with checklists and they get to the point where they simply follow the checklist and believe that by following the checklist, they're doing the right thing. The checklist is there as, think of it as a guardrail. It's not there to tell you what to do. It's there to help you to avoid some mistakes that you might make. The second icon that I've got here is intended to show you that you're managing risk. One of the companies that I was privileged to talk to about 15 years ago managed their entire company by this. And what I mean and what they meant by risk is that you take what you're building, break it down by a lot of the subtasks, and identify whether those subtasks are unique and the difficulty level associated with them. And part of what you get from that is a nonlinear score, and manage your company by trying to drive down that overall risk. What this does is it forces you to focus on areas that are difficult, and it makes you focus on them early rather than focusing on them late. It's very easy to get caught up in making progress, but not necessarily making real progress. And the third icon, I told you I'd get to that. The third icon was meant for me to tell you, this is, as I said to people joking at the beginning, everybody needs a pony in their particular presentation. And what I mean to show here is that no successful company that I know of is a one-trick pony. So what you need to do here is realize that in building a company, what you're doing is building this whole process of going through a build, measure, learn loop. You're going to do this multiple times. And what you want to do, of course, is to get better as you go along. So with that, I'll turn it over to Raul.
Yeah, so when we started Silicon Catalyst roughly 5 years, a little bit over 5 years ago, it was a time when investment in semiconductors was actually fairly low. In particular, venture capitalists were very reluctant to invest in chip companies because there was a feeling that chips were becoming more and more of a commodity, number one. And number two, there were alternatives investments which were much less risky. This is epitomized perhaps by apps which could be built in a very short period of time. You could get to a demonstrator or a first viable product in a matter of months, while, as we just learned from what Mark showed you, right, it takes a few years to actually build a chip. And so we decided, well, obviously innovation is necessary in semiconductors. We need semiconductor solutions, we need chips. And so what can we do to remedy that situation? One of the first things we did is we went out and we interviewed a lot of startups and semiconductor companies and asked them, what are your issues? So if you just look at the issues, they look all pretty much equivalent, right? There's none that stand out dramatically. If you look a little bit closer, right, you see that as a matter of fact, EDA and lab tools, which are of course necessary to design chips and the prototype builds, are a little bit more weighted than all the other issues that you go there. But once you go to expenses and challenges, actually the picture becomes much clearer. If you look at expenses, right, one of the key things is of course raising money. The second thing is managing your time. Of course, the longer it takes to design a chip, the more likely you are to run out of money. And if you look at the challenges, right, then very clearly EDA tools and the silicon prototyping are the things that dominate it. And so we went and thought, what can we do to help with this? And next slide, please. And the answer is actually pretty obvious, right? If we can provide the tools, which are pretty expensive, a typical tool set to design a chip, a state-of-the-art tool set, depending on exactly what you get, right, can cost several $1 million. And so if we could provide the tools for free, the intellectual property, chips these days are built not only by designing from scratch, but the large majority of the area is typically occupied by things like memory cores and ARM core, and maybe a RISC-V core, IOs that you don't build again, you reuse them. And if we could also provide for free, not only the tools and the IP, but also a path to fabrication, a spot on a multi-project wafer, then a company would need to raise much less cash, next please, than if they had to fund all this. If you had to fund all this, EDA, IP, the testing of the chip and the fabrication of the chip, you're going to spend most of the capital that you raise, not on just the team, but also on acquiring all of these. If, however, an incubator could provide all this as an in-kind contribution, then you need much less cash. The rest you raise as in-kind, and the cash that you spend, as is illustrated there in red, goes towards actually hiring the people and developing the product, and not so much into essentially spending on things that are collateral, that are absolutely necessary, but that don't really contribute to making your startup more or less successful. Anybody can buy these things. So what we did, next please, in Silicon Catalyst was we went to the industry, next. We went to the industry, right, and we recruited Inkind Partners. Now, this is a result after 5 years. We started with very few. But if you see, we have different categories of Inkind Partners that provide their tools or services or goods for free or for a very steep discount to a company that wants to design a chip to our portfolio companies, right? And examples among them that are really important are EDA companies. You see Synopsys there, you see Mentor there, Ansys, Silvaco. So you can get their tools for free for up to 2 years, which is a good period to get started, perhaps a good period to actually get even to a prototype. In terms of IP, we provide the two most prevalent cores here, ARM and RISC-V, in the form of Sci5. We also have Synopsys, R cores, and all their other IO IP, which is great. If you go to services, we have a few companies that actually does services that can help you design your chip. Perhaps the second most important one after EDA, right, which was the fabrication of the chip. We have TSMC, which gives you free shuttles if you're building a company, so you can get a prototype built, and ST, which is one of the most advanced MEMS producers, right? If you're doing a chip which requires MEMS, or if you're doing a MEMS solution, right, you can use ST to prototype that. And in the same vein, we have in-kind providers which help you with the test and which help you with business. Perhaps interesting, right? We provide time in the cloud. Amazon is a partner of us, so you can get AWS hours for free to run your tools, to do your designs. We also partner with Rescale, which has a couple of tools, in particular the Ansys tools and the Mentor tools in the cloud, so you don't even need computers, you can just run them in the cloud. Next. This has resulted in a lot of companies. We have over 30 portfolio companies, and many of them, and they're listed here, actually come out of universities. You can spot, if you look carefully there, 2 of our portfolio companies which came out of Stanford, but we also have portfolio companies which came out of MIT, which came out of Cornell, which came out from Montreal. We have several companies, as a matter of fact, in Canada, etc. So if you are thinking of building a chip company, Silicon Catalyst is a great place to start, because we will provide you with all the in-kind, with all the collateral that you need for designing a chip. And we'll also connect you, of course, to an ecosystem of over 100 advisors that have been there, have done that know how to design chips and know also how to commercialize them, and how to figure out what is your market and how to hit the market properly, as Pete was explaining in the beginning. Next. And I think that was it. Join us in driving innovation. Silicon Catalyst is there for you if you want to start a semiconductor solutions company or a chip company. Thank you.
Thank you, Raul. Thank you, Mark Eisers, because of our excellent relationship with Stanford, with professors like Dennis, with Kurt Peterson, with Rick Barr, with Boris, with Mark Horowitz, with a lot of the folks at Stanford. I think in our network, there's probably 4 or 5 that regularly lecture at Stanford. That we would provide office hours to talk with the entrepreneurs that are interested in putting together a company and providing advice as to what they should do next before they jump hot and heavy into building a startup. So, and with that, I think that concludes the presentation. Thanks again to Dennis and to Mark and Raul. Over back to you, Dennis.
Thanks so much. Are there any questions out there? I have one, and it relates to a project I'm currently involved with, and that is, how do you guys deal with that? People who want to build things which don't use a standard process.
What do you have in mind exactly? Is this MEMS related, or is this, or is this?
Let me take a shot at that.
A part where the actual process does not utilize design rules and that sort of thing by any of the foundries.
Tough question. You think about it, Raul, while I'm trying to answer here. So clearly TSMC, as the largest and highest volume and most advanced foundry, doesn't really like to do anything custom. We have gotten them to do implant changes and a few other things. Sometimes you can get them to do non-custom things by the way that you make your mask and so forth. But we also have relationships with global foundries and with smaller foundries, some that are official partners and some that are unofficial, like global. So we would talk with you and we would try to figure out where it would make the most sense. And a lot of the smaller foundries are a lot more, flexible in terms of doing these things. But again, it's never easy. It takes.
Yeah, well, that's the answer I expected, and would have been surprised if you'd said otherwise. But this positions the silicon catalyst process into basically building parts out of known quantities in the most efficient way, which is perfectly reasonable.
I'd like to add that in the MEMS arena, clearly there's no one foundry like TSMC in MEMS, right? ST is considered to have perhaps the best foundry, and they're our partner. Bosch also has a very good foundry, and they're our partner. And there are other foundries around the world that do MEMS. And so what we try to do is find what the startup is trying to build, and then tailor it to the capabilities of a foundry and then go work with them. But in some cases, it's a lot of work at the foundry too. So in some cases, they're not going to do it for free, or they're not going to do it. But we definitely give it a good shot. And we've been quite successful at getting startups into MEMS foundries that never before they would have gotten in.
Yeah.
But
we had
on the silicon side,
one of the companies that was there on the slide that came out of Stanford Seminar, right? They actually don't use a standard process. They try to use as much of a standard CMOS process as possible, but they're trying to do like a one transistor RAM, which is a static RAM, right? Which is of course a very different thing of what the industry is doing right now. And they've been in the incubator for a while, right? We've connected them to both foundries, right, and customers that are interested in that kind of thing, and they've made some progress. So we have done things like that, right? But it's much more difficult. If you don't need new materials, if you can use the fab as is, and all you're doing is changing the design rules and perhaps doing something a little bit different than using just a run-of-the-mill PDK, that works fine. If you want to introduce new materials and a different manufacturing process, that becomes a lot more difficult, of course.
Yeah. So does that mean that you guys are not staying right at the bleeding edge of semiconductor technology, but in operating in an area where things are more stable?
No, I think it's different, right? To look at that. One thing is material innovation, which is of course very interesting, right? And process innovation, but that is much more difficult, right? Than actually constructing system in silicon. And our main goal is, of course, enabling companies that want to do a solution in semiconductors using existing processes, not so much develop new processes.
Makes sense.
Sure. I was wondering, in your experience, which is the greater risk? The risk of not delivering to the plan, the execution risk, right? Not delivering the chip that you intended to build, or the risk of trying to build the wrong chip, the chip that the market doesn't want?
I would say that based on a lot of experience, building the wrong chip is the most common, right? Even at large companies.
I'm completely with you.
Yeah. Even at large companies, I've seen people trying to build a comm chip with everything but the kitchen sink in it, and first of all, bring it. It's not competitive because it'll use too much power. It'll use too much, too expensive from a silicon area and yield. So I think the most common is building the wrong product. And that's why we focus so much on product market fit and talking with customers. And I did want the previous question.
I find it in that context, I find it strange that, you know,
Go
I've
ahead,
been on
Peter.
the entrepreneur side of the table, probably over 100 VC meetings by this time. And almost all of those conversations all focus on the execution risk. And I just find that strange.
I think they all believe that if you have the right team, that you will find the right product. I think the collective experience among all of the people here says that that's not always the case. The other point that I would make that I think is important to note of what Pete's saying is back to that timing question. You can build exactly the right chip, and if you build it 5 years too early or you build it even a year too late, it's the wrong chip. So it can be wrong for reasons of it's got the wrong feature set, or it could be simply that your timing isn't at the right point.
Yeah.
Yeah, those are good
I wanted to add 2 comments to Dennis's first question, which is we have expanded beyond the initial launch with silicon to semiconductors. We've expanded to intellectual property. We've expanded to MEMS and sensors. And we are considering expanding into materials. We're not there yet. Our joint venture in Chengdu, China has already expanded to materials for power, like nitride, so carbide and so forth. But we have not decided to make that step, but we're seriously considering it. And then the other thing is, we'll go out of our way to help the startups. We have a major tier 1 foundry that's not TSMC, where we've been able to negotiate, sometimes even at the CEO level, to get basically production mass sets discounted and then converted to equity for the startup companies. So you know, when you talk about changing processes, you know, we'll take a chance at negotiating pretty much anything. We're not always successful, right? The more custom, the harder it is, but we'll do that.
I think we covered everything. Thank you guys for giving the presentation. I hope your wisdom finds a welcome ears somewhere, and things will work very well for you.